Hello to all IoT 2020 participants. I would like to present our paper titled Natural Language Goal Understanding for Smart Home Environments. My name is Mahda Noura and I'm a PhD student at the Technical University of Chemnitz. This work was done in collaboration with my colleagues Sebastian Heil and Martin Getke. One of the main objectives of the Web of Things, and in particular the smart home domain, is to enable end users without expertise to control their smart devices to be able to fulfill complex tasks. This is also known as end user development. One of the most popular ways of achieving this is through multimodal voice interfaces. You may be familiar with the most prominent examples in the market, such as Amazon Alexa and the Google Assistant. The normal process for such voice interfaces is shown here. First, the system receives the spoken utterance from the user as input. For example, it's too dark in this room. And then this voice input is converted to a text form, and a set of natural language processing techniques is applied to identify the meaning of the user utterances. And finally, a suitable solution for the user is executed on the physical devices, which in this case may cause the smart lamp to turn on to improve the brightness in the room. However, there is a big challenge in the process that we just saw. To understand the meaning of smart environment utterances and provide a good user experience, there is some challenges. One of the main challenges is that the NLU model needs to understand the different types of expressing goals. However, this is challenging because of the diversity of the natural language. You can express the same goal with different and numerous grammatical structures. For instance, if you want to express the goal, I want to reduce the noise level in this room, you can express it in numerous ways, like it's too loud in here, the noise is bothering me, please reduce the volume, or even quieter. By looking at the existing works in the literature, we notice different levels of utterances in the smart home domain. Here you can see the pyramid, device commands, direct goals, and indirect goals. The difference between these levels are the amounts of information that is specified by the user. This information tends to decrease towards the end of the pyramid. So let's look at some examples here. For instance, device commands can be turn on the heater. These commands are like existing systems, like if this and that. They are strict commands where you give to a specific device. And then we have direct goals, which do not explicitly specify the target device, such as increase the temperature. We also have indirect goals that are utterances that contain even less information and are formulated instead in a goal-oriented manner, such as I'm freezing here. In this case, the users don't command the device, rather they are stating the overall effect that they want to be achieved in the physical environment. This BPMN, which is a grammar-based approach for understanding spoken user goals in the smart home and converts it to machine representation, which can then be used by external applications or services like artificial intelligence planner to identify a possible solution for the goal. In our proposed approach, there are two roles. We have first the natural language engineer, and then we also have the WISH natural language parsing. Using the first four steps of this process here, the engineer specifies the grammatical structure of utterances according to a set of patterns. Each of the identified pattern is represented using EBNF rules. All the rules together form our WISH grammar G, represented here, which is a context-free grammar. For more information, please read our paper called WISH, which was accepted at the International Conference on Web Engineering 2020. Then in the next step, in step 5, there needs to be done labeling for extraction and classification. The extraction is similar to POS like tags to enable extracting smart home entities such as device, the action, location, quantity, and so on. Also, some information that is not directly specified in the utterance can be identified through classification, which requires us to further label the generated utterances with classes that correspond to a physical parameter like temperature, humidity, and so on, the effect type, whether it's an increase, decrease, the scope, or the goal type. The second role is the wish natural language parsing, starting from step 6 to 10. This is an automatic tool chain for supporting end users by automatically extracting and classifying the necessary information from the user goal. What happens is that first the user specifies their goal using audio, and this goal is then converted into a text. Then the utterance is parsed according to the wish grammar. And then in steps 8 and 9, the responsibility is to assign the correct entities and intents for the utterance according to the specified grammar. For our application, I will provide some sample voice utterances as input, and as output, the system identifies the entities and intents. Turn on the TV. As you can see, the goal is type device command. The device is TV and the action is turn, and the device state is on. Let's try it with another goal. Play the movie Titanic. This time the goal is direct and the action is play a movie, and as value we have Titanic. Let's try this time an indirect goal. It's too hot here. This time the goal is indirect, and the effect that the user wants is to decrease the temperature, and the location is also identified as here. These machine representations can then in the next step be used by external applications like artificial intelligence planners to generate solution for the goal and put the device actuation on physical devices. To assess the quality of the proposed approach for extracting the entities and identifying the intents from a user goal in the smart home domain, we collect goals from the end users in an online survey. The online survey presents the user with a hypothetical smart home scenario. After this data set was cleaned, we ended up with 253 goals in total, which was then manually labeled by us to provide the ground truth. Here you can see the distribution of the data set in terms of the different type of goals. So we have 114 device commands, 69 direct goals, and 70 indirect goals. The bar chart here shows the number of unique locations, action, devices, concepts among the total goals that were collected. Of our proposed approach based on the ground truth, our proposed approach has a precision of 0.9 and it has a medium recall of 0.5. This is due to the nature of the grammar-based approach. If an utterance is matched against the grammar, it will be completely correct, leading to a high precision. And if there is no match, it is counted as completely incorrect. While a higher recall and a lower recall variance would be desirable, we believe that a higher precision, as is achieved by the wish parser, is more important in the smart home. For instance, assume when the user interacts with the smart home through natural language and they issue an utterance that the system doesn't understand. Of course, this is annoying for the user and it leads to a lower user experience, but it is still acceptable. But if an utterance is wrongly understood, which is equivalent to having a lower precision, it is less acceptable, since it can potentially cause several device actuations in the environment, or worsely, it can provide harmful actuations that cannot be redone from the user side. So taking this into account, and what we see here from the F measure 0.5 of achieving around 0.81 represents a good performance, and we can conclude that the wish parser is actually suitable for extracting the relevant concept in the smart home. F1 score and the precision recall curves. As you can see here, the wish parser achieves almost a precision of 1 throughout the entire recall range, whereas the recall is always between 0 and 1. This is due to the fact that the utterances that we collected from the users are very verbose and very complex. For instance, utterances like, "I feel moody, play me some songs." In this work, we proposed a goal-oriented voice interaction mechanism for the smart home environment. We saw that the results achieved a high precision and a medium recall. For future work, we intend to compare the grammar-based approach in this work with deep learning techniques. We intend to use the wish data set for training our model. Thank you very much for your attention. Please contact me for any feedbacks or comments. And also you can find all the proposed approach artifacts, including the evaluation data set and the wish grammar on our project page stated here.